Suchetna can go to the full screen mode, no? Now.
Yeah. We'll start in a minute. Okay, so I think we have our quorum. So let's start. This is IUCAA's Thursday Colloquium, which has been going online for, it seems, eternity right now. And we now have this every other week instead of every Thursday, as we started off last year. I'm very happy to welcome Dr. Suchetna Chatterjee today for our colloquium. Suchetna is an assistant professor at the President's University in Kolkata. She did her PhD at Pittsburgh, then was postdoctoral fellow at Yale and in Wyoming, before coming back to India and joining presidency as faculty almost 7-8 years ago. And she's been doing an amazing thing in getting undergraduate students to do quite a lot of amazing research. And I hope we'll see examples of that in her talk today. She's one of the NAICs, the National Astronomy representatives for the IAU. There are 5 right now from India. And recently she got the Best Teachers Award from the Indian Association of Physics Teachers, the Dinabandhu Sahu Memorial Award, which is a very distinguished award. Welcome, Suchetna. I'm very happy to hear from you about feedback. Floor is yours.
Thank you, Professor Raichaudhuri, for this very, very kind introduction. Actually, it's quite an emotional moment for me, because exactly 10 years back, that was 2011. Can everybody hear me properly?
Yes.
Yes. So back in 2011, that was actually June 2011, the last time I gave the IUCAA Colloquium, and I was a postdoc looking, visiting places in India. And so I made it a point that maybe in 10 years, I should not be repeating any of the slides that I showed in that grand auditorium. I mean, I would have loved again to give the talk in the auditorium, but probably, some of the audience are common, so some of the slides will be common, but hopefully we'll get to see some new stuff that I and others with me managed to do in the 10 years. So this is really, it's a great moment for me, and I would have really loved to do it like offline, but okay, this is good enough. So the topic of my talk today is feedback from active galactic nuclei, the cosmological perspective. And the first figure that you see, it's kind of has become the poster child of the field from these people, Brian McNamara and Nelson, when they did these phenomenal observations. And I have to tell you that our director, Professor Shomak Raichaudhuri, is an expert and has done extensive work on these systems and exactly these observations when they started mostly in the 90s, late 90s, 2000s, post Chandra era. So today I'm going to show several results, and we're going to discuss about things that we have many colleagues in IUCAA working in. So I'd be very glad if we can have more interactions at the end. Now here what we see is that there is this outflow that is coming from the center of this big cluster. This is a cluster seen in X-rays in blue. So you can see the optical image, and the blue is the Chandra X-ray image. And then this red is the VLA radio image where you see the outflows. And Professor Chaudhuri tells me that now there's a more beautiful image with GMRT. So next time I give the talk, I would probably put that figure. Now, this was a fantastic observation that came out from the superb angular resolution and capability of Chandra in the 2000s, and the cluster community, the X-ray community were really, excited about, and then several other systems in clusters and groups, these outflows were detected from the central supermassive black hole. Now, that's a fantastic observation. Now, I'll just immediately shift a little bit gear, and here what I'm showing you is something that we have colleagues like Asim and others working on extensively. This is exactly an old snapshot from the Millennium simulation where this is just dark matter simulation only, and this is just a snapshot of a massive dark matter halo. And what this is again in the 2000s, it's 20 years old slide. So what it essentially tells us is that how a structure is formed in the cold dark matter scenario. So in the hierarchical structure formation scenario, we form these massive dark matter halos. Now these two are, so what I showed in the first slide and the second slide are not connected, but since I'm telling you, the first slide was probably the nicest picture of AGN feedback, and then we come to the cosmological perspective of that. Okay, that's great. So we can run these beautiful simulations, wonderful simulations, and get fantastic results. And then this is another wonderful observation. There are a set of observations. I'm just showing one result from the gamma survey, which is galaxy luminosity function. So the previous slide was about mass, and mass dominated by dark mass, and this is light. So galaxy luminosity function. This was actually gamma is a multi-wavelength survey, but this is optical galaxy luminosity function. So that's light. That's a structure we see through our electromagnetic eyes. Great. Now again, another beautiful observation that also came around the same time as these feedback systems of these outflows were seen with the extra observations, but completely in a different context. And this is the famous MBH sigma relation. So what this plot shows, this is of course a later observation. This first came from in 2002 by Tremaine et al. And then in 2001, this other group, I forgot the name, but these early 2000s, when people observe these correlations, the correlations are such that you look at the galaxy velocity dispersion, and you look at the central supermassive black hole in these galaxies, and somehow it seems like the mass of the central black hole, which is probably only occupying solar system scale or maybe parsec, maximum sub-parsec scale volume. That's where the black hole's activity or the black hole's sphere of influence is restricted to, but somehow the mass of this system is correlated with the velocity dispersion of large-scale gas and stars. Now, this is, of course, a puzzle because the galaxy, the stars and gas in the galaxy would have no way to know, because this central supermassive black hole is only a very small fraction of the mass of the entire galaxy. So the gas and stars have no reason to feel its presence, which are like what, kiloparsec, tens of kiloparsec scale systems. We're measuring it from a much larger scale than the scale of influence of the black hole. So that's a question. But what it brought us is this paradigm. Somehow it seems like that maybe we could connect the central supermassive black holes with the evolution of these host galaxies. Now, I showed you just 3 discrete observations, and I showed you a snapshot of a numerical simulation. This cartoon picture, this is taken from Joe Silk's, one of Joe Silk's review article, is now people have understanding of the mass function. So this is theoretically, they understand the mass function of dark matter halos, okay? And then you can have some relation of mass to light. And so you can essentially, theoretically, from a hierarchical structure formation scenario, we can predict the luminosity functions of galaxies. So that's theory. And then this blue is what I showed you from the Loveday et al. Paper and many such other observations, is actually the galaxy luminosity functions as observed in these surveys. And then what was seen is that at the low luminosity region and at the high luminosity region, this is the Schechter luminosity, there is a discrepancy between mass to light as predicted by theory and as seen by observations. So there came now what people try to do. I'm going to talk only about this aspect. So what people try to do is that what we see is that we are forming less luminous galaxies. So when we go to the high luminosity end of the galaxy luminosity function, we have less number of galaxies in number than we would otherwise expect from structure formation scenarios. So then people introduced this idea of AGN feedback. And the idea was that this AGN is heating up. There's an additional heating source, non-gravitational heating source, that's actually additionally heating up the gas and halting star formation. And hence, we have less number. Of course, the low luminosity side was, the model that was used to describe this discrepancy was supernovae feedback. And we have Professor Subramaniam and others. My colleague Shomadeep Shamoy also works on supernova outflows at Presidency, my colleague. So this is to describe the faint end of the luminosity function. So now the connection of this M sigma kind of thing came into much more deeper understanding that, okay, so maybe these outflows that were seen in the X-ray observations and radio observations, they got somehow linked to the overall cosmological evolution of the galaxy luminosity function. That is it possible that AGN feedback that we see now in clusters and group scales, maybe it's a very ubiquitous phenomena cosmologically, and maybe many more systems are actually experiencing the feedback from their central supermassive black holes. And that gave rise to this paradigm that we call black hole coevolution. So the key question in this paradigm is that, this is a cartoon picture. This is actually the same slide that I showed 10 years back. Sorry for that. So here there is a central black hole. This black hole is sitting in its host galaxy, and in the paradigm of galaxy formation, this galaxy is sitting in dark matter halos. So now the question is there any connection? Of course, we saw the M sigma relation, so definitely there's connection between the host galaxy evolution. Well, yeah, it's still debatable. We will discuss more in this talk. So is there a connection between the central supermassive black hole with its host galaxies and host dark matter halos? So that is the large scale question that many people try to address through different ways, different aspects. Now the method that I'm going to talk about in this talk, and I have been extensively using, is actually cosmological simulations. So we saw that snapshot from the Millennium simulation, and that was like many years back, 20 years back. And so, of course, the cosmological simulation has emerged extensively from there. People had ways to do hydrodynamics. That means they can now model galaxies. And then, of course, when I was a graduate student, this was back in 2007, 2008, the field evolved in a way that people, after these M sigma type correlations were studied, after these fantastic, majestic observations of AGN feedback were seen, people, the computational cosmology community, included supermassive black hole growth and AGN feedback into this cosmological volume simulation. So this is one of the first simulations that I had the opportunity to work with during my PhD days by Tiziana Di Matteo and et al. This is actually the Volker Springel, the gadget group. And so this was an older simulation. And of course, it has gas, dark matter, stars, and black hole growth and accretion. So now this is I don't know how well this simulation is being, the left side is being visible. What I'm showing here is actually the blue distribution, that's dark matter, and the red points that you see there are the supermassive black holes in this entire box. And then this is a much better picture, the right-hand side. This is actually the projected density distribution of gas, and this is at redshift 3, and the color code is the temperature of the gas. So red is hotter, blue is colder. So what you see is red, the more red is actually hotter gas, and you can see exactly this kind of clumpy structure that we also see when we look at dark matter. And these yellow circles that you see are the supermassive black holes, and the size of each of these circles is proportional to its mass. So we do see that now we have a tool to connect the overall distribution of SMBH with dark matter and SMBH with gas. Okay, so but then the point is, which I will not discuss today that much, but the main point is that just a few slides back, I said that the influence, the scale at which the supermassive black hole is important. Let's say the accretion disk, that's probably few AU size maximum. Even if I go to the BLR region or something like that, it's maximum like a parsec scale system. Now, question is, what is the spatial resolution of these cosmological volume simulations? So this is the Tiziana simulation, was a few kiloparsec, actually a couple of kiloparsecs. So then came this question that we have a resolution, spatial resolution of kiloparsec, right? How are we resolving the physics that is happening at parsec to sub-parsec scales? And that is again a big debate that started from that time in the computational cosmology community. Of course, I'm not part of it, but we can discuss if someone is interested. Now, I just gave 2 lines that black holes. So I will come to that, but just I'm saying that these simulations have supermassive black holes, as we see, and these simulations have a certain model of accretion and feedback from these supermassive black holes. Okay, so I'll come to that how is that done? Okay, what happened? Okay, now this is a clumsy slide, but I think I have to discuss this. I could have made it probably better. So I use this word subgrid models. This is exactly the thing that I discussed previously, that we have parsec scale, sub-parsec scale physics going on, and we are seeing its effect at kiloparsec scales. Okay, so the physics is happening below the resolution of the grid or spatial resolution of the simulation. So there's an extrapolation involved. Now, how that is done, I will not discuss, but the more important question is that we can have these cosmological volume simulations with these subgrid kind of models. But then why don't we run? So we have Dipanjan Mukherjee, for example, uses beautiful, at IUCAA, our colleague, he does these wonderful jet simulations. We had Chris Reynolds talk in the IUCAA Colloquium. He's one of the leading experts to study numerically the jet ICM connection. So those are isolated simulations, okay? Now, what is so somebody can ask me a question that, what are you interested in studying? Are you interested in studying the interaction of the outflows with the gas surrounding the black hole? Are subgrid models good at that? My question is no. Isolated simulations are better at that, and these isolated simulations can, in so much high resolution simulations, and they can have more detailed physics modeling. So of course we have the more basic hydrodynamic simulations, and then you can have MHD, because you can, so for example, the Dipanjan simulation, if you have seen this magnetic fields, so MHD, and then if you can even go be very brave and try to do GRMHD. Okay, so these are simulations where you actually study study the interaction and the microphysics. Definitely, none of these are possible in cosmological volume simulations. Then what do I do? What are cosmological volume simulations good at? And here is the question, that the reason we run cosmological simulations is exactly what I said in the beginning, that to study galaxy evolutions. So to study large-scale environments of these galaxies, these co-evolution paradigm, make mock catalogs of black holes and host galaxies and host dark matter halos, create sample statistics. So if I want to study the overall cosmological perspective and the importance of these SMB8 systems in large-scale structure, then cosmological volume simulations are the way to go. If we really want to study the physics of feedback, then I would go for isolated simulations like the kinds of Chris Reynolds and others are running. But these ones are fantastic when we want to study the co-evolution paradigm, okay? So now, as I said, the physics is below the resolution limit. So we have subgrid models. Do you believe them? My take is, of course, depends on whom you ask. So if you ask the cosmological simulation community who run these feedback simulations, they definitely believe it and love it. But if you ask someone like me, who's more of a phenomenologist, my answer to that question would be, yes, I would believe it to the extent that these simulations, even if they're subgrid models, how good will they be in describing observables or observations? We have to construct observables of different kinds from these simulations and see that how are these models that are included in the simulations, subgrid ones, actually match. So this is the ultimate test of fidelity of this model, are the observations. And that's, so now you can define, you can define lots of, you can actually find lot of observables. For example, we just saw in the previous slide, Joe Silk's cartoon of the galaxy luminosity function. So you can make galaxy luminosity function. You can even make, so you can make AGN luminosity, study AGN luminosity function. One can study AGN mass functions. One can study M sigma type correlations and their redshift evolutions. So there are multiple observations that one can construct from these cosmological volume simulations and then go and test with the real universe. Now, that's where a little bit of my contribution comes in, because I'm going to describe that what kind of observables we have looked at using these cosmological volume simulations and what we extract from that. But before that, I just like to just give a list. This is a list of so this was 2008 when first these simulations came into the community. But then, the field evolved, and there were a lot of debate at the time that, some people don't believe, some people do believe. But then, of course, in the next 10 years, the field evolved very well. And these are a large number of simulations that came online, that came to us. So the ones that I marked in red, Massive Black 2, which was run by Nishikant Khandai. So he's many of you know him. He's a faculty member at NISER Bhubaneswar. And then this one, Simba. These two simulations are the ones that me and my students, my group has used for predicting observables. Now I have also marked the famous one, the illustrious TNG, because we also had Volker giving a talk, and we also have plans to use illustrious TNG to test some of our predictions. Now, as I said that it could be a talk on how do we implement feedback and supermassive black hole growth into the cosmological volume simulations. Since I'm not talking much about that, I would at least give you a list of very important questions that come when we talk about SMBH in the context of cosmological simulations. So first is, how do seed black holes form in the universe? That's an unknown question. So how do you implement that in your simulation? How realistic are the models of accretion? You are not resolving the scales. How realistic are your models of accretion, and how does it affect your observable predictions? What role does resolution play in modeling the accretion physics? What is the microphysics for coupling of gas and AGN outflows? Very important that we are talking about AGN outflows. Now, it could be either radiation or particles. How do that couple with the surrounding gas? So again, as I said, since these are below the resolution limit, so these are very important questions that come again and again to us when we think about comparing with observations. And then finally, a little bit more technical, that is the feedback model that we are using, or what happens in the real world? What about radiative feedback or mechanical feedback? Which systems are more prone to having radiative feedback? Where do we see more mechanical feedback? For example, the beautiful McNamara Nelson picture that we saw, that's definitely mechanical feedback, because you're just pushing the gas. But then there can be radiation, and that radiation can also couple with the gas and reheat the gas. Okay, so these things require a lot of thought, and many of these simulations actually very effectively sort of modeled all these issues when they came up with the results of the simulations. Okay, so for my part, now I'll get into that the observables that I have been I shouldn't say it's actually my group, and these are pictures, these are photographs of my students who contributed extensively on what I'm going to talk in the next 30 minutes or something. So Rudrani Kaur Chaudhuri, she just submitted her thesis. Ovinanda Chakraborty is also a PhD student, and both of them are very, very proud to say that both of them actually did the IUCAA graduate school, and the training they got here was enormously helpful for them to come out with their thesis topic. And of course, Shomo Rai, who was an undergraduate and master's student at Presidency, and now is a graduate student at IUCAA, contributed extensively, and these are my collaborators. Okay, so Professor Rai Chaudhuri was talking about the contributions of UG and master's students. So I'm going to just Shomo, for example, is one of them. Some other work I'm going to also discuss a little bit. So now the simulation parameters. So I said that, so DiMatteo et al. Was an older simulation, and this was a small box simulation, 34 megaparsec size box. So it has less number of particles. See, this is the softening length, and the spatial resolution was of the order of some few kiloparsec. And then Kandai simulation, the good thing about Nishikan's simulation was it was very much like the DiMatteo et al. Simulation, except it's a much bigger box. And so we could have more statistics, we could have more luminous AGN in the box, and we could go to higher mass halos, cluster scale halos, to study the effect. Now, as I said that we have subgrid models to simulate the black hole growth, what we can do is we can study now. So we have everything at our hand. We have the dark matter halos, we have the gas properties, their temperature, their density, metallicity, other properties, and of course we have the supermassive black holes and their properties, their luminosity, their mass, etc., and other things that you can derive. So our next order of business is trying to model the emission. So I'm going to just describe. So what we did is we just looked at the surrounding medium and studied the emission mechanism. Now, again, this slide is actually taken from Rudrani. So you can imagine that this is a massive computational work, and Rudrani was terrific. She did all this programming and writing the code and doing everything, but none of those was possible. None of those would have been possible if we did not have access to the IUCAA clusters. So I must thank IUCAA and also my associateship program, for which we had access to IUCAA, and particularly during the pandemic, we could sit at home. Rudrani, particularly, she did the leading work here, sit at home and do the simulation. So big thanks to IUCAA. This is just the level of complexity of the problem. Now, what Rudrani did in her work, and what we tried to do is, we tried to look at the gas properties in the simulation with and without feedback. Now, in a real universe, it's very difficult. We cannot really decouple that, okay, this is how it will look if there isn't feedback, and this is how the gas properties would look if there is feedback. But in a simulated universe, we have that benefit. So we have the same set of two simulations. We start from the same initial conditions and have other properties exactly the same, except in one case there is AGN, there is SMPH growth and feedback. In the other case, there isn't SMPH growth and feedback. So now you have two similar systems and you compare. And this is just one example of, now you can see that this is a SPH simulation. So otherwise there is a little bit graininess that you see in these maps. That's because we had a small volume that we simulated. It goes away if I have a larger slice, but this is a 50 kiloparsec by 50 kiloparsec projected temperature map of two systems. So let me tell what this picture is. So the upper one, okay, so the upper part is two halos. The left hand side is low mass halo, the right hand side is high mass halo. This has a mass of about 1.6 times 10 to the 12, something around that, and this is about 8 times 10 to the 13. So this is a group scale, very small cluster scale, mostly group scale halo, and this is even less massive than a group scale halo, the host halos. Now in the top panel, the AGN is present and AGN is feeding back their energy into the intra-cluster or intergalactic medium, in the interstellar medium. And what we see is that regardless of the mass of the halo, this is just one system I'm showing. So what we see that regardless of the mass of the halo, even if it's small scale, it's larger scale mass, we do see that the temperature of the gas is increasing, because that's normal, that's common sense also, that in the presence of feedback in all mass scales, in all mass scale halos, the temperature of the gas is definitely increasing due to feedback from the AGN. Now, if I look, I haven't put it here, but we can look at it later. So if I look at the density, actually the density distribution is very different, because once we include AGN feedback, the gas gets more dispersed, and the density in the presence of feedback actually lowers, whereas temperature increases. Okay, so that's what we found extensively in the simulation. So that's a theoretical thing. Now, what do we do with this? We looked at temperature, we looked at density, we looked at other properties. But then what we tried is we wanted to calculate the X-ray emission that's coming from that, the diffuse gas. And for that, Rudrani used APEC, the Astrophysical Plasma Emission Code. So we had a cosmological simulation. Now you have to know how to couple a cosmological simulation. And a lot of this work is also done, a substantial amount is done by Shomo, who is now a PhD student at IUCAA. So what APEC did is, we just input into APEC the gas properties from our simulations, from the Khandai simulations, so the DiMatteo simulations. And then APEC produces an X-ray map. APEC calculates the Bremsstrahlung emission, the radiation recombination, all these processes, it calculates from these parameters. And we then get an X-ray map of the system. Okay, so this is, for example, at redshift 1, pretty high redshift in the Khandai et al. Simulation. This is an AGN with this is the mass of the AGN. This is the AGN is sitting at the center. Now I have to be careful to tell you that we did not calculate the X-ray that is coming from the AGN itself. So from the accretion disk of the AGN, we did not calculate that X-ray signal. It's just the X-ray that you get from the diffuse gas surrounding the AGN. And the mass of the black hole is 3 times 10 to the 7 solar mass. This is just an example X-ray map of that 50 kiloparsec by 50 kiloparsec region that we get by using APEC. And this is one system. So what we did, or what Rudrani mostly did, is she looked at all the black holes. There's like thousands of black holes. Tiziana simulation had about 3,000 black holes at redshift 1. I think 2000, around 2,500 to 3,000. This is a small box volume, but Nishikant's is much bigger than that. So you look at all these black holes in the simulation, you compute the X-ray map, and then from these X-ray maps, you calculate the surface brightness profile. Now, there is a lot of bookkeeping that, so you do the same thing for the without feedback case, because we have also the simulation where black hole feedback is not present, and then do a static analysis and try to see that is it possible to sort of see any difference in the X-ray profiles of these systems accreting versus the ones that doesn't have feedback. And what we find is that, yes, we do see difference, but then this is very high redshift. So observationally, the scales, this is, so if this is 50 kiloparsec scale, in the 10, 15 kiloparsec scales, we do see that there is underluminous, so similar to the extra cavities that was seen in the McNamara observations. I did not describe much about that because it's probably widely known. And so we kind of see something similar to that, that we do see that around the AGN or around the black hole, it's underluminous in X-rays. And this is for the same reason, because the gas is getting heated. It's also getting additional kinetic energy. So it goes away. And as a result, there's less supply. So as a result, the accretion of the black hole also shuts down. And since the gas moves away, the density falls, although it's hot gas, but the density falls. And as a result, the X-ray emission in these systems generally falls when there is feedback versus when there is no feedback. So the X-ray emission goes down, and kind of see this cavity kind of thing, okay? So that's great. Now, what Rudrani did is, so this was just apex. So you just model the theoretical emission that is coming. But then if we want to see that what we measure from the simulation theoretically, is it possible to look at it from current and of course future X-ray emissions? To do that, what Rudrani did is she used the MOX simulator. So this is basically a mock observation, synthetic observation kind of thing. So you take the theoretical map, and then there is this mechanism where you actually use all the telescope parameters into your theoretical map, and then make a photon map. This is a Chandra photon map of the same object at redshift 1. Now you can see that the structures are not, we are not able to resolve the structures in this map, because this is pretty high redshift, and that's why the angular scales are very small. But in Rudrani's thesis, I didn't show it here because the thesis is still under examination. So if I do the similar analysis at lower redshift, then we actually have much better resolution from Chandra. This is redshift 1 is very high, so much better resolution in the context of the theoretical models, and we do see that probably it's kind of detectable with Chandra kind of telescope. So we do see these structures. So the whole idea is that we now make mock maps, mock X-ray maps of systems where we have AGN feedback and systems where we do not have AGN feedback. And then we see that in a survey, if we have many such systems, first, by doing stacking analysis, we can just look at something like the surface brightness profile. And also, if we look at individual systems, we have an observing proposal of the TCAP AGN with Craig Sarrazin and Mark Lessey, where you actually look at the individual systems, you identify individual systems and try to see that if there is an active accretion going on versus there is no active accretion, do we see difference in the X-ray map of the gas surrounding the black hole? So this is 200 kilosecond, it's an expensive Chandra synthetic observation. Of course, if you increase your exposure time, maybe you get more signal, but this is, we did 200 kilosecond because we wanted to compare with some observations from the AG survey. Now this is, so what I showed you is we looked at the Khanda et al. Simulations, and we looked at the DiMatteo et al. Simulations, which had some specific subgrid model to have black hole accretion and feedback into the system. But then, as I said, that these are subgrid model, these are evolving. So what we did in addition is that we now this is Rudrani has started, and we have some of the preliminary results. We looked at an even more recent simulation by Dove et al. The good thing about Dove simulation is it's the same box size as Khandai, but the good thing about the simulation is that it has multiple models of feedback. For example, Khandai simulation actually only have a spherical bondy kind of accretion, and the feedback is isotropic, whereas Dove has different modes of feedback, including this conical jet kind of model in their simulations. So what we try to see is that, okay, we have this prediction of X-rays. How much are this prediction robust to the kind of simulations we are using? And so this is actually a comparison of a similar mass black hole. It's kind of, I think it's close to roughly 10 to the 8 solar mass black hole. And also the halo mass scales are similar. Of course, they cannot be exactly similar, but kind of similar. And Rudrani just computed the X-ray map, and let's see. So this is the K15 X-ray map of the system, and this is both at redshift 1, and this is the Simba. And what we see is that this Simba, you see, it's very smooth, unlike the K15 one. So we need to see that how come this is so smooth. But the good thing is that the scale of X-ray flux, the geometries, definitely this is very smooth and very spherical kind of geometry, whereas here we do see the diffuse kind of system. So but what is inspiring is that, at least what is optimistic, is that the scale of signal that we get from these two simulations are same. And of course we have to also perform the mock simulations of Simba and then K15 and see that, okay, because if I am to, and also, as I said, that this is a Chandra simulation that I'm showing you, but our plan is that we also want to use Athena, which is a future X-ray mission, to see that to what level, first of all, to what level can we understand about feedback through this, that is being predicted through these cosmological observations. The other reason, I use the word fidelity. So the other reason is that also it's a great thing for the computational cosmology community, because we now have yet another observable which sort of tests that which sort of is a test of these feedback models that are being used in the simulation. So what we learn from that, we have to see once the observations come and we are capable, how much capability we have in explaining them, we can have more input in improving our own modeling in the context of cosmological simulations. Okay? So that's great. Now, the other observable that I'm going to talk about, so that was X-rays. Okay, so essentially, majorly thermal bremsstrahlung simulations, bremsstrahlung emission. The other thing that we tried with this simulation, this was actually part of my PhD thesis. So this was looking at the same system, but not through X-rays, through the Sunyaev-Zel'dovich effect signal. What is that? Now, the Sunyaev-Zel'dovich effect is the inverse Compton scattering of the CMB photons through hot electrons that is present in the line of sight of the CMB. Now, we all know that this was first described by Sunyaev and Zel'dovich, and this has been widely studied in the context of clusters, galaxy clusters, because galaxy clusters have copious amount of hot electrons which inverse Compton scatter the CMB photons, and we do see a spectral shift in the spectrum of the CMB. And with this spectral shift, we actually see decrement, enhancement of flux, which comes as cold and hot spot in the CMB. So that's a fantastic observation. And the great thing about the SZ effect is that since we are looking its distortion with respect to the CMB, we have a delta T by T term, And as a result of that, it's actually redshift independent. So no matter what is the redshift of the cluster, if its parameters, its mass, mostly mass, and other parameters are same, we do see the same effect regardless. So what the good thing about is, but then it has some other issues. I'm not getting to that. But now in this context, in the AGN feedback context, we had this proposal many years back, seems like a century to me now. This was my first paper, where we tried to say that, okay, we have these outflows coming from the AGN, and that also have hot gas. So what if these gas, introduces a spectral shift in the CMB, in the cosmic microwave background, and if that is at all detectable. Now, at that point, when we proposed, actually there were others who proposed of this effect before us. What I actually particularly did in my PhD thesis is trying to look at this effect from theoretical models and numerical simulations. We used Tiziana simulations at the time, and tried to see that, is it possible? At that time, ACT was coming online, and now we have so many results from ACT. Even Planck was, on the flight, so we did not have Planck results. Definitely not ALMA, the one that I'm going to talk about. So what we predicted is that, is it possible to detect the signal with microwave background experiments or sub-millimeter experiments that were coming online at that time? And this is just a power spectrum that we predicted. We had some models. This is a theoretical, this was an analytic model. We did the same using numerical simulations also. Now, one of our predictions was that if this effect actually happens from our model, whatever modeling parameters we had, we predicted typically a microkelvin level signal. Now, it is important because a cluster SG signal is 100 microkelvin. Okay, the distortion is delta T over T is of the order of 10 to the minus 4. Here, we are talking 2 orders of magnitude small signal. But of course, one has to remember that this signal is dependent on the model that we are using in our analytic formulation or in our numerical simulation. For example, what kind of subgrid model am I using in my simulations? And this was our prediction that, ALMA, this was an ALMA prediction for an integration time of an hour, that if ALMA, we just predicted at the time ALMA was coming online, the ALMA compact array, ACA, the ALMA compact array in its compact configuration should be able to detect this signal if we do a long integration observations. This was 1 hour, but these parameters were tentative at the time. So that was a prediction we made, that it is possible, probably, for ALMA to test that what we are talking is real or not. Is this signal at all detectable? Is it a real signal or not? And then I'm very glad to say that many years later, this is in 2019, so we had these predictions in 2007, 2008, and then 10 years later, Mark Lessey, this was led by Mark Lessey, and this was probably one of the proudest moments in my research career when we actually had a direct detection of this signal. Now, apart from direct detection, we also predicted that there could be cross correlation. So we can detect them with cross correlations. What is that? So suppose we have the CMB observations, and suppose we have a large sample of quasars, let's say from the Sloan Digital Sky Survey. And then if we can cross correlate the CMB maps with the Sloan maps, so the Sloan quasars, for example, there is a chance that we can detect this effect. And then back in 2010, again, this was part of my thesis, we just had some tentative detection. We could not call it a detection for multiple reasons. This was using WMAP. That was the WMAP era. because WMAP also did not have the kind of angular resolution that we're talking about. WMAP had a 30 arc minute sort of angular resolution, and we were talking about effects that were 10 to 20 arc second scale effect. If we go back to the, if I go back to the power spectrum, these are the models that we predicted for SZ for quasars, and you can see that this is a very, very high L value. Sorry, around 10 to, around like, so we were actually getting around like 10 to the 4, so 10,000. So it's a much smaller angular scale where one would expect the effect to dominate. So WMAP was definitely not optimized for that. But then later, after many years, this was very, much ahead of what we could do at the time. But then later, from many of these groups, with Planck, ACT, and SPT, there were many detections. There were detections of cross correlations of signals of SZ from quasar feedback or AGN feedback. But then in 2019, we had the first detection via ALMA, again, the ALMA. And when Mark actually approached me or the project and said that we are interested by your paper, we are inspired to do these observations by your paper, I was so happy because all my life I thought that this will never be detected. But then we had the first detection. But I have to tell you that this is a single system where we could detect the SC effect from feedback. So now then again, how is this SC effect coming in the context of what I talked for? The cosmological volume simulations. The idea is very interesting because in a cosmological simulations, I have thousands of AGN, right? Thousands of simulated AGN. And just like I could do an X-ray analysis, I can compute the Y distortion, the Compton Y distortion, and the temperature distortion thereof from a single accreting system or multiple accreting system, and I can build the statistics of what could be the SC distortion. Yes, we did some pioneering work many years back, but now we have a bigger volume simulations. We have more simulations with different models of feedback, and so this is one example of this. Abhinanda, my PhD student, and Shomo, they have done quite, they're just doing this work. Abhinanda is leading this work. So here is an SZ map. This is a flux map. This is an SC map, but this is a much bigger region. You can see 300 kiloparsec by 300 kiloparsec. And this is an SC signal map. This is in Jansky. And what you see is here the central black hole. And here is what is coming from the outflows, from the diffuse gas around the black hole. So that's work in progress. And what is exciting is that we now have ALMA fully commissioned. We have NGVLA coming online. I previously spoke about the extra experiments, but then NGVLA, ALMA, these are experiments which are actually optimized to go for direct detection. We just had one single system where we detected SZ effect from outflows, from AGN feedback or quasar feedback. So here again, I'm just showing you the map of, this is an SC map that I showed previously, and this is the X-ray map from APEC for the same system. So now this is enormously exciting that now I have cosmological simulations. I have a system of black holes. I compute their SC flux. I can compute their X-ray flux. And then I can use the mock observation technique. We have not yet set up. It's under preparation. It's going on. We still do not have the full mechanism to do mock observations for NGVLA or ALMA. Abhinanda has just set up the system, but we still, again, it's all done through the IUCAA cluster, I have to say. So what we can do is, we know that how this system will look through NGVA, or how this system can be observed through ALMA. And then we also know that the same system, how will it be observed through Chandra or Athena for that matter? And then we can do a cross-correlation analysis, because SZ is pressure n times T, whereas if I think of Bremsstrahlung or for X-ray, then that's n squared T half. So the dependence of temperature and density is different. And this sort of, if we can do joint analysis, that will give us more constraint on what kind of feedback energy we are talking about, what kind of outflow geometry we are talking about, and stuff like that, which again will be the fidelity testing for our cosmological AGN outflow models that we have. Those are subgrid models that we have in our simulations, okay? And as I said, that's cosmological simulations are extremely important for this purpose, because just one single system won't mean much unless we have the large scale, perspective. So we have this large sample, and also how overall gas is coupling to the system, what is the dark matter halo, all these things come into picture, and that can only be achieved if we use cosmological simulations other than isolated simulations that I talked about. So I think, how much time do I have? So
you've got 5 minutes, Ashish.
Okay, very good. So I'll just briefly, since we are talking about cosmological perspective, and I have only discussed about outflows and X-ray and SC signals from these outflows, the other thing that one can do, I mean, there can a lot of things people can do, but the other thing one can do is what about the host dark matter halos of this system? Now, in simulations, we have knowledge about the host dark matter halos, how the halo mass function of host halo mass functions of AGN evolve over redshift, etc., etc. But then observationally, can we test the models? The answer is yes. And I will just briefly say something, because this I actually spoke a month back on 29th June. I gave the colloquium at RRI, and here is the link, the RRI colloquium. And now in the online days, you really cannot give the same colloquium again and again. So I had to little bit change my stuff, because there I mostly spoke about the host halos. And again, these are the BSc and MSc students who contributed. All of them are PhD students now in this work. And what we actually did is we used the halo occupation distribution formalism. And what the halo occupation distribution formalism is, I'm just briefly, quickly going through it. So we have the cosmological models. We know what is the host dark matter halo population in the universe. And then, of course, the unknown territory is models of AGN growth, black hole growth and AGN feedback. This gives me dark matter halo population. Now here, let's say in the simulation context, from this, I can have a probability distribution. This is probable. So the HOD is essentially a probability distribution of the number of AGN, and you can select AGN based on any property. Here I have just used AGN luminosity of number of AGN in host dark matter halos. And of course, the spatial distribution of AGN within individual halos. So these you get from your model. You combine those two, so you know the dark matter halo population. You have a prediction of the probability distribution because you have the simulations in your hand. Then you can predict AGN clustering. However, observationally, we do the reverse thing. We have measurement of AGN clustering, and then we use the AGN clustering observations to extract the probability distribution, the HOD. That means the host dark matter halo properties of our AGN. And then we compare that, does it match with what we predict from our simulation, from our analytic model, or whatever. So that's how we can have knowledge about the host dark matter halos. And I'll just very quickly, this is a beautiful AGN unification picture, the Uri and Padovani paper. And if I gave the colloquium offline, and just outside the IUCAA lawn, we had this beautiful structure of the unified model of AGN. Now, this was work done by Kostab Mitra, who was an undergraduate and master's student, and he did it as his undergraduate thesis. He's actually looking at the host dark matter halos of obscured and unobscured quasars selected through the WISE survey and trying to find out the distribution, the distribution of host masses of both obscured and unobscured quasar. What was the goal of the project? The goal is that if we have AGN unification, that means obscured and unobscured are just orientation effects, then there is no reason to have different large-scale environments of obscured and unobscured quasars. If it's more than orientation or different from orientation, then we would expect, if we see differences, then we can tell ourselves that, oh, really, maybe there's something beyond orientation. So if anybody is interested in this talk, I would really ask you to actually look at the YouTube link that I said, but we can talk about this later. And what Kostov find, I'm very briefly saying about it. So what Kostov find is that if I look at the large scale clustering properties, so in this figure, this is actually central and this is satellite. So what Kostov found is that if we look at the large scale clustering properties of obscured and unobscured quasars, then we do not see much difference in their host halos. But then there's something called the one halo term, that is the, sorry, the satellite distribution of AGN within their host halos. And so there also we could not find much difference. The reason for that was WISE clustering measurements were not good below the 1 megaparsec scale. So we did not have good measurements to make predictions. But the key point, I'm really fast on it, so I don't know how much I'm getting across. But what Kostov did is he actually made a projection that suppose I have smaller errors on the small scale clustering measurements of these WISE quasars. There he found that although the large scale properties tell me that their host halos are almost similar, so its orientation is good, orientation is respected through the large scale clustering properties. If I look at small scale clustering properties, I do see significant difference in the host masses of obscured and unobscured quasars. Now, so you can have, and then so what could be the reason for that? And we propose some evolutionary model using the Hopkins paradigm that it could be this merger business. And if we really want to make more testing, we also propose some observations. I'm not really getting into the details of that, but the takeaway message is that orientation is not everything when we try to understand obscured and unobscured quasars. So now I'm really at the end of my talk. So cosmological simulations have been successfully modeling black hole feedback, several observational signatures. We discussed about X-rays and SZs that we did from our group. And of course, the next avenue is doing joint analysis of X-ray and SZs, particularly through the mock simulation, mock observation technique. And of course, we have a number of X-ray and submillimeter missions coming. So this is exciting opportunity. And in the context of host dark matter halos, I have to tell you, there's one other thing I wanted to say, but I knew that I'll not get time. It's highlighted in my RRI talk. The last thing we discussed is that we tried to test AGN unification model, the orientation-based unification model through the HOD aspect. And we saw that orientation is not the end of it. And this is some other thing. This is direct measurements of HOD because there are theoretical biases in the model. But I think I like to end the talk by telling that a huge lot of things in the front of looking at host dark matter halos and galaxies and gas properties can be done using cosmological volume simulations. And this is really an exciting time in the interface of theory and observations, where we can extract and understand more about AGN feedback and its cosmological context. Before I end the talk, I just want to show you this illustrious simulation. Now, let me see if I can use the Zoom. Just a sec. So I'll just stop share for a minute. And I have to use the just a sec.
The sound is not that important. You can just
okay. No. I think I can. I did have the sound. So share computer sound. Let's see. Share. Now, can you see the simulation?
No, we see your you see your slide back again.
My slide. Okay. So stop share. Just one sec. Let's see how can I share the screen. Oh, okay. Let's see this. Share. Can you see the simulation now?
Yes. Well, we see a YouTube page.
Sound there?
Yeah.
So this is the illustrious simulation, and the AGN feedback aspect is there. This is just dark matter. So thank you very much. Now,
great, thank you. Thanks, Chitna. You can stop sharing if you want.
Yeah.
And it's great to see work done, of course, by an IUCAA associate and the students right from undergraduate, MSc as well as PhD students, and then using also IUCAA facilities. Wonderful for us to see. Thank you very much. And I'd ask people to use the raise hand option which is under reactions now. And please raise your hand to ask questions.
There is somebody typed a question.
That's okay. I mean, we'll go to that first, but Dipanjan is asking a question. Dipanjan, go ahead. I'm unmuting you.
Hi, Shoshana. This is a fantastic talk and a fantastic set of results. It's especially nice to see the results from this young master's and bachelor students and doing some fantastic work. It's great to see that. I'm still trying to get my head around the various implications of the results. So I may come back to you later, but a quick question on the first part of the talk, where you were trying to find the X-ray of the nearby gas on the galaxies. So I'm not surprised that you have different results from two different simulations, because if you're aware of the Agora project, they try to compare different schemes. Each of these codes have different schemes of injecting the outflow, etc., etc. But for a given simulation, what difference do you get in the X-ray profile as a function of the black hole mass? I'll tell you my motivation for this. We have mostly focused on AGN feedback for high mass galaxies. Now we know how things behave. But now, as with low-fast surveys, we are trying to push the limits. We find that there are several FR2 galaxies now with low luminosity going beyond the thing. So I'm sure in future surveys we'll come across more cases where lower mass black holes will also start to contribute. And focusing this on the large scale cosmological simulations and what kind of predictions they might have from the observation perspective is important. So given the X-ray structures you're trying to find from these simulations, what happens when you go for a distribution of black hole masses?
Yeah. So nice question, Dipanjan, very nice question. Now, so when you are saying low mass systems, what kind of mass are you referring to?
I'm saying you start going below the knee. So we've always focused on 10 power 5 and above, so 10 power 11 solar mass galaxies. So start moving below the knee. So if you look at the thesis of Amy Rines, they're finding aliens in dwarf, I won't say they're typical dwarf galaxies, they're 10 power 10 solar mass and for 9 solar masses. But you will have black holes in there. So in these large scale simulations, this is something not looked at. Do they also have some implication on the environment and heating the environment of the gas?
So let me get to that first. So since I did not really tell in detail that how are these black holes seeded in the simulations, because we don't have any model of initial mass functions. We don't know the theory. So one of the limitations of this simulation is that the way you plug in the black holes into the simulation is that you have these halos on fly, and then, so suppose depends on the mass resolution of the simulation, that what you call a halo. Let's say you call 10 to the 10 solar mass. So it's about, if the mass resolution is roughly 10 to the 7, 10 to the 6, then maybe 1,000 particles when they assemble, you call it a halo. So maybe 10 to the 9 solar mass, that you resolve it as a halo. Now, then there is a limitation that what can be the mass that you seed in a 10 to the 9 solar mass halo, because that's going to be constrained by what you see in the M sigma type relations. So when you say this lower black hole systems, what we did in our models, it's a good, very good question. What we did in our models is we actually had a cutoff of the black hole mass, because our seed black hole mass was close to like 10 to the 5 in the Khandai simulation. I think Dave is a little lower than that. I'm not sure fully. So we actually wanted to look at systems that have mass substantially higher than the resolution limit of the mass. So we looked, for example, 10 to the 6 and beyond. In fact, better, when Rudrani in her thesis actually looked at systems 10 to the 7 solar mass and beyond. And the answer is that when we look at this X-ray, let's say the geometry, that how this X-ray emission that we see in these maps, that really doesn't depend on the mass of the black hole. What matters is how active is the black hole. So if we have even a smaller system, but it has like strong outflows going, it's actually accreting at the Eddington limit, then you just do see that gas is being moved away from its surrounding and the X-ray emission is lower. So I wouldn't really say mass. Yes, mass and accretion have some relation, but it's more, you can say that it's more of luminosity of the black holes that determine that how much displacement of the gas that we are going to see and how is it. So it depends on how much displacement we see, what is the distribution of energy and temperature, that is going to determine how it will look in the X-rays, because that's what is being input in the APEC. But then if you really want to ask me that what will be the effect if we go to really low mass limit, 10 to the 4-ish, that we still don't have.
I was not really asking about 10.4-ish, but the mass ranges that you talked about were the ones I was most interested in. Yeah, maybe I will get in touch with you later, because this has also implications for the dragonfly kind of galaxies where you have dark matter dominated.
That's right. That's right.
Anyway,
that's right. So, yeah,
very nice stuff.
Yeah. Thank you. You're muted, I think.
Nishikanta Khanda is also here. Did you have anything to comment in response to this? I don't know whether he's around. Suchitra, there's in the chat, there is a question before I go to Shantanu. There's a chat in the question from Prathapratim Deka. Can you read it?
Yeah. So thank you. So can one invoke AGN feedback in low luminosity galaxies? Very good question. Along with supernovae feedback, will mechanical feedback be more important in those low luminosity systems? Good question. So first is yes, you can have, but so for example, in the context of simulation, as I said, it's really coming to the resolution limit, because I think the point when you go to 10 to the 10 solar mass halos, if you go below 10 to the 10 solar mass halos, then results, I don't know how much reliable. I think the reliability is questionable. So yes, you can implement, but is it possible to implement? The answer is, so we have AGN feedback everywhere. In fact, there is also supernova feedback in our simulation. So we have AGN feedback in all accreting systems. Now question is your second part. So probably that's the first part of your first answer to your first part of your question. For the second part, will mechanical feedback be more important? Now, what we see typically is that if we look at cluster scales, clusters, galaxy clusters and group, there we do see these large outflows and this mechanical feedback kind of thing. So it is not understood that is there really a reason that why we see these massive outflows in cluster scale halos and not in smaller mass halos or smaller galaxies? So I really don't know the answer. At least observationally, what we know, mechanical feedback seems to be more important in higher in cluster scales, in clusters, rather than low mass galaxies. In galaxies, mostly we do have this quasi-wind isotropic kind of simulation. But this is a important question, that do we see mechanical feedback and radiative feedback at equal footing? Is there any reason that one is dominating in certain kind of systems and the other is dominating in certain kind of systems? I really don't know the answer to that. That requires more knowledge. Does that answer your question?
So yeah, actually the radiative feedback that you're talking about can also not be, I think, decoupled from mechanical feedback, because
right.
if you're doing the energy transfer through bubbles, that is mechanical
right.
in nature, right? Because you're doing work against.
So, well, in the simulation, we don't have really, that's not radiative feedback, because we just, increase so we just dump energy into the gas and give it more thermal energy. So it's essentially like doing more work. So it's essentially mechanical feedback in the simulation. But yes, so we, in our simulation, we do it for all systems. And as Shomak said, that it's not always possible to decouple one from the other.
Yeah. Dipanjan's already put a link to one of Joe Silk's papers, which actually addresses part of this with low luminosity, low mass galaxies. So that would be wonderful. Let's move on. Shantanu, your question?
Yeah. Can you hear me? Yeah. So,
yes,
so you've done a very nice talk. I had actually requested some of my students to make sure they attend this talk, and I'm glad they attended. So anyway, I have a very basic and high level question. Obviously, I mean, this is very, I think, difficult and all that. But so you started the talk with M sigma relation. So my question is, okay, maybe I missed it if you answered it. So after all these simulations, which I think you are doing and many other people are doing, and can you actually explain the M sigma relation? And I just have a quick follow up. Let's say you can explain all this, but I'm still see the M sigma relation, right? It's a very nice, deterministic, pristine relationship, very low internal scatter, and the kind of physics models which you put in, I think they are like non-linear, stochastic, dissipative process. But yet somehow the way I see it, right, everything sort of magically cancels, and you get a very pristine relationship. So I guess if they can explain, so what is going on, and can you get an analytical understanding of this?
Okay, Shantanu. So here is it. First of all, the first thing I have to say that I don't run the simulations. I use the simulations run by people. The second is M sigma relation is not a relation with low scatter. Actually, there's a lot of scatter. The slope depends on what kind of systems you are looking at. Is it elliptical galaxies? Are you doing measurements through the gas velocity dispersion or the star velocity dispersion? How are you measuring the mass of the central black holes? Is it through some scaling relations, or you are looking at mega measures, or you are doing reverberation mapping? So I wouldn't think that it's a low scatter relation at all. There is a correlation, that's definitely true, and that's interesting. Now, in the context of the simulation, let me tell you that how do we explain the M sigma relation there? Now, one thing people do is, so when you model the feedback, you actually, in the simulation, what is being done is that when we model the feedback, we actually dump a fraction of the accretion energy of the black hole into the surrounding gas medium. So let's say m dot c square is the energy, and a fixed fraction of it is being dumped through a smoothing kernel into the surrounding gas. Now, what fraction should we dump is actually a free parameter in the simulation. Now, what some of the simulators did, or at least the pioneers like Di Matteo's group, they did is they ran a bunch of isolated simulations and sort of tuned the feedback fraction to such a number such that it kind of explains the local M sigma relation. Now then you can ask me that suppose I tune my feedback parameters and explain the local M sigma relation, then what I can do is I can look at the M sigma relation at other redshifts, because I have matched it with local observations. So I can look at other redshifts and see that with that same feedback parameter, do I get something like an M sigma relation that matches with the measurements that is done at higher redshifts. Now, your question is that regarding the smoothness of the relation. So what I think the basic physics here is that we have this, we have the gravity, right? So we have mass, there is mass accretion going on, and then you have a fixed fraction of that energy through outflows or through radiation coupled to the gas surrounding it. So the question is that sigma is the velocity dispersion of stars and or gas, whatever you call, but the fact that we are dumping additional energy into the surrounding medium, that affects star formation, that affects the dynamics of gas and stars. As we saw in the simulation, that we have a different temperature distribution, we have a different density distribution. So that's how you kind of relate. Now, probably your question is that mass accretion is a, so exactly what your question is, that it's a stochastic process, but how do I get a smooth kind of relation? But I said that it is smooth, but there are definitely scattered to it. The reason that we get it is because the gravitational binding energy of the gas that's been coming to the black hole, the center of the galaxy or the cluster, that is disrupted. So the gas escapes that that field because the gas gets additional heating or additional energy that is coming from the outflows. That's how that first order relation is established. Now, of course, as you said, that there are lots of scatter and depends on what kind of system, depends on how feedback happens. It's not really a very smooth relation. I think, I don't know if I answered your question appropriately. Is that?
Let's wrap up, Shuchitan. I think, yeah, I think you did. We are running late, but Surud has a question. Let's see if you do the question. Surud, you're unmuted.
Hi, Suchitna. I'll just quickly ask the question directly. So this HOD modeling that was performed for the obscured and the unobscured quasars, I just wanted to know whether you had checked what is the stellar mass distribution of these obscured quasars, like the hosts of these obscured and unobscured quasars, was there a possibility to actually try to link them to galaxies through other surveys?
Yeah, so this is a very good question. Now, we don't know the host galaxies of the obscured and unobscured quasars. In fact, so my short answer is that no, we don't know the host galaxies of these objects. It's just that they are infrared selected AGN and we looked at their clustering properties. But it is possible finding the host galaxies of obscured quasars. I don't know how that can be done, but it's possible. But the answer is that no, we don't have the stellar mass distribution.
Right. Yeah. I mean, the reason why I was asking is like sometimes these sample selections can also seep in and change the clustering properties, right? So I guess what you're saying is whether it's obscured or unobscured, if it has the same IR luminosity, then its clustering is different. Is that's what?
Yes. So it's selected. So it's selected through IR.
Right.
So it's selected through IR, and its redshift distributions, etc., are similar. But host galaxy properties of these
we don't know.
Yeah, these systems are not known. And then you look at their so the selection was based on the IR luminosity of the AGN itself and of the quasar itself, and then you look at its clustering. Yes.
Okay, thank you.
Since people are still around, I have a very, very quick question. See if you can give me a quick answer. It's hard to know because you're putting in black holes in a cosmological context, what you can get out of it and what is actually something you put in. So one of the ways that you detect these AGN in different parts of the spectrum, say whether it will be seen in X-rays or in radio or in optical, depends on the Eddington ratio, right?
Yes.
And so is that something you get out of this, or is that something you put in?
So what no Eddington ratio actually you get out of it. So the way it's done is that you have this dark matter halo, you have this black hole, and then there's a Bondi accretion model. So the black holes can grow through Bondi accretion, which is spherical accretion, and they can also merge with each other. That's how the mass grows. Now, what will be its luminosity? That's you have m dot c square, but you know m dot is dependent on the ambient temperature and density and velocity property of the gas. So then what will be its Eddington ratio? That actually comes out from the simulation. So yes, you can extract the Eddington ratios. Yes.
Wonderful. Thanks. It looks like there are no more questions.
I think there is one from Alokar.
There is one chat box. Okay, go ahead if you want to address.
So do you think it's relevant to use detailed feedback and ISM modeling, but small box simulations like those of Kim Oestreicher's Tigris in making the analysis you are talking about? If so, when, then in what aspects such detailed modeling will be useful in the context of your work? Detailed modelings are definitely very useful from the context of all work. Yes. So Kim and Oestreicher actually. Kim and Oestreicher's work that involves, you're saying, small box simulation with much higher resolution and more modeling. Yes, that would be very useful. But again, if we go to small box, we lose the large scale context or the large scale environment properties. So in certain ways, it's very useful. In certain ways, it's not useful. Really depends on what is the question we are trying to answer. Does that answer your question, Olankar?
I don't see anything in YouTube either, except appreciation from Miradi. Okay, so let's, it's 5:30 already. Oh, Olankar says, yes, it does. Let's thank Suchetana for an excellent talk, and what a wonderful discussion after that as well.
Okay, so thank you so much. So I have to again thanks IUCAA so much for first inviting me to give this talk. This was wonderful. And secondly, of course, the whole work had so much to do with the help and the privilege that I got being an IUCAA associate. So thank you very much. And thank you, Shamogda. Thank you.
Thank you, Suchetana.
Thank you very much. So maybe can I leave now?